Ramanujan for G is now available on the Google Play Store. Try it out for free.
Hi students. So good morning. Good morning. So today we are going to look, do a brief review of DC power first. I want to do a brief review of DC circuits a little bit before I move to AC circuits. And obviously this is just a revision. I'm not going to redo the full DC circuit story. But then I'll very quickly switch once I get some of it across. So with respect to DC circuits, we looked at basically the two laws. One is Kirchoff's junction law, and the other is the Kirchoff loop law, right? Junction law states that current coming in equals current going out. Loop law states that if you go once around a loop, you will get the voltages will go back to zero, right? These laws still apply. They just are done using a different kind of mathematics. Current law still applies. Junction law still applies. Okay. Loop law also still applies. Only thing is that this term resistance is going to give way to another related term, and we will discuss that term when we get there. Okay? But remember what we did. You go once around the loop, you end up with zero, right? This plus that plus this plus that plus this plus that, zero, right? Like that, right? I'm sure you remember the problems that we did. We did several numericals not so long ago. Okay, so how we did various problems, then how we discussed how to solve problems like which involve multiple circuits, right? So having said that, and then we discuss what happens in a circuit, in a DC circuit which has a multiple capacitors, right? We introduce capacitors, and we introduce various types of questions of varying levels of complexity, right? So you may remember all this. If not, I suggest how we deduce the loop law and the junction law to solve particular circuits. You may remember all this, but if you don't, my suggestion is for you to invest significant time in solving these questions. Okay? So now the other idea that we carried forward was the idea around power. Power is what electricity is all about. There is and all of you, when we say there is a power cut, right? We have this power cut, and so and then there is also voltage drop, right? Now, what are all these things and what impact do they have, right? We were dealing with all this only so long ago. So let me next look at that, right? So I will now share a couple of screens which discuss that. Okay, so and why do we do this? Why do we little bit go back now? Because we're getting ready for AC circuits, and I want you to remember the material quickly. Okay, so okay, so here look at if you had a pure resistor in a with a voltage source, and there is a drop of voltage across that resistor. VAB is the drop in the voltage across the resistor. So if the direction of the current is this way, in this case that is from A to B this way, then A will have a higher voltage and B will have a lower voltage, right? And the change in the voltage is I times R, right? the drop in the voltage is I times R, right? So, but the corresponding power consumed is I square R, or more correctly, V times I. Okay, and V times I, and V is equal to IR, Ohm's law, right? And and therefore power is the product of potential and current. P equals VI, or I square times resistance. In transmission lines, power is dissipated due to the resistance of a wire. Okay, when we looked at various questions, when we looked at combinations, etc., the more lines you go, the more power is dissipated. Okay, so having shown that, I'm going to now come to the material around today's lecture. Okay, so so today we will continue with this discussion on AC circuits. So in an AC circuit, let me maybe so in an AC circuit, we first started with a recap of Faraday's law and Lenz's law, and then we then introduced Lenz's law. We said that, so basically Faraday's law states that when there is a time varying flux, magnetic flux, there is time varying magnetic flux, there is an induced EMF, and that induced EMF is in the opposite direction, and it tends to oppose the change in the flux. Okay, therefore, so now, having got explained that, now we then introduce this idea of like the kind of source that is generated by a AC circuit. That is, we put if you remember, in Faraday we had this north and south magnet, then we put this loop in the middle, and then we rotated that loop, right? It would, when you rotate that loop, it would produce a sinusoidal current, because the B, if you remember, the B times the dot A is that led to a sinusoidal wave, right? Therefore, you ended up with a time varying current, which we call alternating current. Okay, so that because the as it rotated, it would go this way, and then the power would go this way, and then the power would go that way, right? And as you rotate it, it when it's 180 degrees the other way, then the power will go the other way, because the north and south are fixed. This one rotates, so it will go, therefore it produces a sinusoidal wave, right? So it's you may and it repeats itself. Now, how many times it repeats itself is the frequency, how fast that switching goes. The frequency in India, we tend to have 60 hertz. In the US, we have 50 hertz. India, we have 60 hertz, and then the corresponding omega is 2 pi f. So if you have 50 hertz, it's 2 pi times 50 is about 300 omega, something like that. And then correspondingly, we also have the VM, right? VM is when we say 220 volts, that is related to the VM. Okay, so now you put a resistor in that circuit like a bulb, and so when you put something like a bulb, or what it does is it then sucks some current, converts it to a light, some of it to heat, right? And therefore it pretty much behaves like some kind of a resistor. Okay, now so VI equals V by R sine omega t, right? And so it's just a what you call these are all of these are like a resistive element. Now what happens when you put a resistor, a single resistor circuit, right? Basically, as the voltage goes up, the current goes up. V equals IR, right? As the voltage goes down, the current goes down. And you then have this, V and I, peaking and going to the lowest point and hitting 0 all at the same time. When we have that happening, we say that they are all in phase. Okay, and then we draw this kind of a thing which is called a phasor diagram. Okay? A phasor diagram basically it discusses how things rotate, and how fast it rotates, is this angle is omega t. Okay, and then you have I, which is one phasor, and V is another phasor. Okay, so for purely resistive circuit, the current is in phase with the voltage. There's no angle difference between the voltage and the current. Okay, not so if you have these other elements like a capacitor or a inductor. But first, then let's look at the average of the cycle. So what is the average current, right? The average current, let's say you had a current of the form Im, where M is the maximum sine omega t, then what is the average current? It is over one period, 1 by t, 0, integral 0 to t, Im sine omega t, right? So that is the average current. So, and when you do that integration, integral of sine omega t is minus cos omega t divided by omega, right? And then when you plug that in, right, you will end up with Im times 1 by omega t times 1 minus cos omega t. So how do you end up with that? You end up with that because 0, what is that? Cos 0 is 1, and at any other point it is minus, and at t at period t it is 1 by minus cos omega t, and the 1 by t is what produces the other t. So Im by omega t times 1 minus cos omega t. Okay, and so what is the average over one cycle? It will be 0, right? Because this should also go to 0, right? Omega t equals 2 pi. Therefore, over one cycle, obviously, one half is positive, the other half is negative, so the total is 0, right? Now, instead of I, if you went with I square R, which is the power, so what happens to the R? It just gets taken out, right? And what happens to the I square? You end up with sine square omega t. How do you integrate sine square omega t? Right, as 1 minus cos 2 omega t by 2, right? So once you write sine square omega t as 1 minus cos 2 omega t by 2, right, and you do the integration, you end up with half. Okay, and so the power is I m square r by 2. Okay, and so now the IRMS root mean square power is Im by root 2. Okay, so so if and the VRMS is Vm by root 2, and so when you multiply Vm times Im, VRMS times IRMS, you end up with Vm Im by 2, right? Vm Im by 2 is this one, average power, right? So IRMS times VRMS will give you the average power. Power average is IRMS square R, right? Okay, so if I gave you the IRMS, you just do IRMS square times R. Okay, so it is like roughly 7.707. What is root 1 by root 2 is 0.707. Okay, so now let's take a look at this one. Sinusoidal and alternating voltage to 220 sine 100 pi t volts is applied to purely resistive load of 50 ohms. Time taken for the current to rise from half of the peak value to the peak value. So how long does it take, right? So that is based on the omega. Omega is what? 100 pi, right? So now from that, to rise, for the current to rise from half of the peak value to the peak value, right? So so half of the peak value is what? Sine theta is what? sine 90 is 1, sine 30 is half, right? So it has to go from sine 30 to sine 9. So if you put 0.5 equals sine 100 times pi t naught, and 1 equals sine 100 times pi t1, right? So you have to, you then end up with 100 times pi t naught equals pi by 6. Pi by 6 is 30 degrees, right? That's from this one, and this one is pi by 2. 100 times pi t1 is pi by 2, right? So the difference between the two should give you pi by 2 minus pi by 6, right? So, and therefore t naught minus t1 is, based on that, you end up with t naught minus t1. Okay. So that's what he's looking for. He's looking for what is t1 minus t naught. T naught is 1 by 600. T1 is 1 by 200. Based on that, you can then, calculate your values. Okay. So the notice that the pi's cancel. Okay. So now, instead of just a resistor, if you introduce instead a purely inductive load, when they see a purely inductive load and they introduce this term L, right, they are not talking about M, which is the mutual inductance, but they're talking about the self-inductance. Okay, so it's like a solenoid, and that has been added to a circuit. Okay. Now, then what is the voltage at an instantaneous basis? Phi equals Li d phi by dt equals minus Li L di by dt, right? So basically that's all you end up with. The change drop in the voltage is L times di by dt. So V minus L times di by dt equals 0. That is the use of Kirchoff's laws in the context of a inductance. Okay, so we're still applying Kirchoff's laws. In this case, we are applying Kirchoff's loop law or voltage law, right? So V minus L di by dt equals 0. Di by dt is what? They take the derivative. You already, you already saw, right? So I equals integral. Therefore, if you had the voltage, where voltage is V sine omega t, right? So if the voltage is Vm sine omega t, then you end up with an integral, right? Therefore, you integrate and you end up with I of t being an integral, right? And the seed in the case of Q is equal to CV, dq by dt is equal to C dv by dt, right? That is in the case of the capacitor, right? In this case, V is equal to L di by dt, okay? Therefore, these are the two differential equations that tell you, about these other two elements in the context of an AC source. Notice that in a DC circuit, a capacitor eventually becomes a open circuit. It just stores charge and there is no current flowing in steady state. There will be current when you first turn on the switch, but it will eventually reach steady state. There will be no current. Okay. Now, the inductor, on the other hand, will tend to act like a short while a capacitor acts as an open, the inductor acts as a short in a DC circuit. In an AC circuit, this is what happens. You end up with this term. Okay. So now they introduce this term called reactance. Okay, we had resistance, and so this is called reactance. Okay, what is this reactance? It's like a resistance. It is written as omega times L. Okay, and so and eventually they are going to introduce a J there. Okay, but that is just peeking into the notes which is going to come later. Okay, so now I equals V divided by omega L sine omega t minus pi by 2. Okay, so why did we end up with this negative pi by 2, and what does that do to this figure, right? What they are telling you is that the V and the I are not like this. Okay, when the V is going up, the I is little bit different. Okay, it is out of phase. Okay, so the I may be coming down like this when the V is up. Okay, that's what they are telling you. That's what this is all about. Okay, and therefore the I and the V are not in lockstep. Remember, V is just V sine omega t, while I is V by omega L sine omega t minus pi by 2. So the pi by 2, right, is what we call the phase lag. Okay, so the phase of the inductive circuit lags. So when this is 0, this is negative. Okay, and when this goes up, this when this is dropping like this, it is then going up. Okay, so this difference in phase changes the phasor diagram like this. If the voltage is here, the current is 90 degrees behind it. Okay, that's the minus pi by 2 there. Okay, so as this rotates, right, as the voltage rotates, the current will also rotate, but out of phase. Okay, so now calculating the power for an AC inductance circuit, power is equal to V times I. So I sine omega t minus pi by 2 times V sine omega t sine A sine B is what, right? So so then an inductor basically doesn't consume any power over a whole cycle. Okay, this is a very important idea. Inductors are not power consuming like resistors. So over a cycle, the total power is 0. It is like a frictionless spring. A frictionless spring, it will go back and forth, right? So pure inductor works like that, as does a pure capacitor. Okay? So now energy is absorbed during one half of the cycle, and all that energy is then returned back to the circuit in the other half. Okay, and so that's what's going on there. Sorry. So we then introduce this term in reactance, which is given by omega L, right? XL equals omega L, and V is equal to IR. Okay, so that kind of an equation. I is the IRMS, and so you then use omega L as your reactance. It is like a resistance in the context of V equals IR. Okay, so now if you had, what happens if you have both? Okay, if you have both a resistance and an inductance, right, then things get a little bit more different. Okay, now you already saw this part of it. It's just a revision. If there's only a resistor, V and I are in phase. If there's only an inductor, V and I are in perpendicular to each other. And he gives an example. Okay, now resistive circuit. Let's quickly go over the example. Resistive circuit is in which RMS value of current is 5 amps. What is the value of the current 1/400 seconds after it becomes 0? Okay, now frequency is 50 hertz, right? So 50 hertz means what, right? So 50 hertz means it changes 50 times a second, right? So if each cycle is 1/50th of a second, so the period is 1/50th of a second, right? So 1/50th is what? 0.02. So 1 divided by 50, right? So in 1/400 is what with respect to 1/50? It is 1/8. Okay? Therefore, here, 5 root 2 amperes, 5 root 2 sine 100 pi t. So, let us see why we end up with 100, right? 2 pi by 2 pi f equals omega. Omega equals 2 pi f. Therefore, 2 pi times 50 will give you omega, right? Therefore, it is 100 times pi, right? So, and what is the I max? The current, when they say RMS current is 5, the I max is 5 root 2, right? Im by root 2 gives you RMS current, which is 5 amps. Okay, so that's how you derive that. Okay, so now he's given another example. V is this. There is an inductor, 10 Henry, right? So what is the omega is 400 rads per second. So what is the reactance? 400 times 10, right? 400 times, and they use the value ohms. Okay. Now Im is equal to V divided by omega L. So 4,000, right? So Vm is 25, right? 25 divided by 400 is I max, right? And therefore you can write that equation. It's out of phase, right? So these are the two equations. Okay, and so now the third thing he introduces is the capacitive circuit. Just as we had omega times L as the reactance, right? For a capacitor, it becomes 1 divided by omega C. Okay. Now, what happens in the case of the capacitor with respect to the phase? The inductor was 90 degrees behind, right? The capacitor is going to be 90 degrees in front, plus pi by 2, right? The other one was minus pi by 2, right? Q is equal to CV, dq by dt is the current, I equals dq by dt equals, therefore it is C dV by dt. Okay, therefore Q is equal to CV is then you take the derivative, V is Vm sine omega t, therefore I is equal to CV omega cos omega t, right? Therefore you multiply the two, CV omega, you end up with I am. Okay, and so that's how this works. Okay, so you can then write I of t equals Im sine omega t plus pi by. So that's how this works. 90 degrees in front, and therefore Im sine omega t plus pi by 2. You calculate the Im, and then here's an example immediately. Okay, so have a single capacitor in a circuit, fully charged. Okay, and the plates are fully discharged. T equals T by 2. The plates are fully discharged. So what happens? Okay, so I leave that to you to calculate. Here's another example. At the instance V of t equals 12 volts, and it is increasing, right? So what is the important idea here? Important idea here is Ohm's law still applies in a different way. There is a phase shift, and with the phase shift, Ohm's law still applies. What is the time lag between voltage and current? Right. You have to spend a little time understanding all this, because if I went into all the details, it will take a little more time. I went into the details for the inductor, the capacitor is very similar. Okay, now power, as I discussed, so here he's having two in series. So if you have two capacitors in series, you have 1 by omega C1 plus 1 by omega C2, right? So now what is the corresponding XC, right? If you have two in series, then it is, you can rewrite it as the total voltage will be from here to here will be the voltage across this and then the voltage across this. The current will be the same, right? So VCI equals IXC1, VC is IXC2, right? Therefore, the sum of these two will add up to the max power, right? Or the max power, right? What is the max power? Max power 25, right? So so using that, you then calculate the current, right? The total XC also you can calculate 1 by omega C1, and this one is 1 by omega C2. Then you add the two, is a 250 and 125 ohms, 250 ohms. Notice that you're adding, although it's in a series, keep that in mind. So you end up with, so you treat it like a capacitor, like a resistor who's with a different resistance. That's it, just 1 by omega C1. Notice that when you do 1 by C1 plus 1 by C2 equals 1 by C, right? You are doing exactly that here. Notice that you are still doing 1 by C1 plus 1 by C2. Okay, that's a very, very critical point that you must note. You are doing exactly that, okay? Because you have to find not the total C, but the 1 by omega times C equivalent. Okay, that's why when you calculate it like this, you then add the two and then you end up with 375. Therefore, the VM is 25, the I max is 67 milliamperes, and then correspondingly you multiply. All right. So, and when you calculate power, you do I times V, Im Vm sin omega t cos omega t, average power. As you might have expected, the average power is going to be 0, right? Power in a capacitive circuit is C dV by dt times V. C dV by dt is I times V, right? And you can rewrite it as half CV square, right? The derivative of V dV is half dV square. Okay, that's what he's saying. So it is d by dt of half CV square. So the power stored in a capacitor is half CV square. Okay, and then charging, discharging, charging, discharging, charging, discharging. Okay, so okay, but the net power is 0 over a cycle. Okay, now if now you introduce an L, C, and an R together, we have what is called an Lcr circuit. Okay, now in an Lcr circuit, you have both an inductor and a capacitor. One is pushing this way, the other one is has a phase which is forward, the other has a phase which is behind. Okay, now there is this idea when the resistor and when the inductor and the resistor, they kind of cancel each other. No, the inductor and the capacitor, they kind of cancel each other. We then say that the circuit is said to be in resonance. Okay, but right now let's not go there. Okay, so now the resistor has no phase, the inductor has a phase of minus pi by 2, capacitor has a phase plus pi by 2. Okay, and therefore now when what we are going to now do is we are now going to introduce this concept that the voltage has with it this a phase. Okay, so Vm times e to the power of I omega t. You all know from de Moivre's theorem that e to the power of I t equals e to the power of I theta equals cos theta plus I sine theta. Okay, now if it was shifted, then you have e to the power of I times omega t plus phi. Okay, now the V divided by the I is going to include all these terms. Okay, and it is also going to include this new quantity that we have brought in, I. Okay, I is what? Square root of minus 1. Okay, so this is a notation that is used to help you use arithmetic rather than use the derivative like before. Here we are taking the derivative, right? Now there is no derivative. You're going to use pure arithmetic in your calculation. Okay, so we then introduce this term called, so inductive load, capacitive load, resistive load, right? We now call all these with one common name, which is called impedance. Impedance is denoted by the letter Z, right? We introduce reactance, right? What was reactance? X. We use the letter X, right? Reactance of a inductor was omega L. Reactance of a capacitor was 1 by omega C. Now, impedance is going to introduce this J as well. Okay. So, what is impedance going to do, right? It is going to, now, if you, when you add this, Im equals e to the power of I times omega t plus phi, right? And so now this Z, right? V of t divided by I of t is V of n by I of n times e to the power of minus I phi. E to the power of minus I phi. Why is that? Because the omega t's will cancel. Okay, so the ratio gives you this. Okay, so now e to the power of I phi, right, is therefore basically it's cos phi plus I sin phi, and therefore it is written as I omega L. Okay, and in the other one it is 1 by, or typically when I was learning this, instead of I we used to use this term J. Okay, J is the same as I, only it's used by electrical engineers. Okay, so they use J omega L. Okay? And now in the other case you have 1 by J omega C. Okay, the Z of a capacitor is given by 1 by J omega C. Now, when you calculate the Z, you have the R plus I times omega L minus 1 over omega C. The R is a real number, resistance is a real number, the capacitance and the inductance is an imaginary number. Therefore, you have the Z, which is the magnitude of the the impedance. It is the square of this, the square of that times the square root. Okay, so you have omega L minus 1 over omega C. Then you have this, what is called an impedance triangle. That is the modulus of Z. Here is the real part, here is the imaginary. It's a standard complex number. Okay, the impedance is a standard complex number. So for this circuit which has L, C, and R in series, we just write this as the impedance. V by Z will give you I. All right, and the same with this I square R. Power will give you I RMS square R. All right, so that here's an LCR circuit. It is actually a differential equation. V of t equals IR plus L di by dt plus Q by C, right? Q equals CV, therefore Q by C. Now, if you differentiate, you will notice that this is a second order differential equation. If you differentiate this one, you'll end up with a second order differential equation. Okay. But normally what you will do is you will solve problems involving LCR circuits using impedance Z. Okay, and so that's the basic idea here with LCR circuits. Okay, now there is a point when so now if you look at this circuit, right, what is the point at which these two things are said to be in resonance? These two things are said to be in resonance when this term goes to 0. This term goes to 0, the Z becomes just R. Okay, rest of it goes to 0. Therefore, you have omega equals 1 by square root of LC. So, at a certain frequency, right, the inductance and the capacitance balance each other out, they cancel each other out. Therefore, the whole circuit behaves just like a pure resistive circuit. Okay, and so so this is this requires some more discussion. There are various types of LCR circuits and filters. So today I'm like going to wind down a little bit early. I'm going to wind down here because if I get into the discussion with this LCR now, it may get a little confusing. I'll just introduce the ideas a little bit. Okay, so the first idea that you need to understand is that in such a circuit, the same rules apply. Okay, you have this circuit, you use V equals IZ. Okay, V equals IZ, and I is also both V and I are also real and imaginary, right? And Z is a complex number. And so now there is a point where the tan, what is this tan phi? Tan phi comes from this figure. Okay, so it is the angle between the V and the I. It is the phase angle between V and I. Now, how do you measure that angle? If you had a complex number, the ratio of the imaginary to the real part will give you the tan of that angle. Right? If you have a complex number, has a real part, complex part, this divided by that, the imaginary divided by the real will give you the tan of the angle, right? So tan phi equals omega L minus 1 over omega C divided by R. Okay, and therefore phi equals tan inverse of the other one. Okay, now if omega L equals 1 over omega C, then tan phi goes to 0. Okay, that means the circuit is in resonance. Now, delta W is this other term, which is related to this other term called alpha. Okay. Delta W is said to be the bandwidth of the circuit. Okay, so typically speaking, a LCR circuit acts as a band pass filter. Okay, so it is, look at the V across R, it is a BP, means what? It's a band pass. Okay, now this an RL circuit will behave like a low pass. Okay, and RC circuit will behave like a high pass. Okay, so using that, you will end up with a huge set of variants, 1, 2, 3, 4, 5, 6 variants. Okay, and so because this is a little bit tricky business, I thought I will continue with this business next class. Although we are a little bit early in completion, maybe I'll go over this example instead of going to the details of this the various types of filters. So in this example, there is a current, there is a voltage V, and there is a RLC circuit in series, right, which has both an R and an X and XC and XL. So the Z is R square plus XC minus XL the whole square, right? Therefore, the R is 80, the XC is this, XL is that, Z is 100 ohms, the VRMS is IRMS times Z, right? Therefore, and that he calculates, from this, right? So the I is, the V is what? V is it is 400 omega is 400 rads per second, right? The 200 volts, right? V is 200 volts RMS, right? RMS 200 volts, and so from this you calculate VR equals IR, V equals IR, or maybe they've given you the I, they've given something here. I think they've given the I, right? Therefore, from the I, you calculate the, the current is 2, right? So from that, you end up with 2 times R. R is 80, therefore 160 volts. VR, VC is, he has 2 times XC. XC, he calculated to be 100, and therefore he has these 3 values. Therefore, the VRMS is this square plus that square. VRMS square is this square plus that square. Okay. So, and the tan of the angle in this case is, XZ by XC, right? You end up with the other one, 200 minus 80, and the R is 160, right? So you have 120 by 160, 120 by 160, 3 by 4, and take tan inverse of 3 by 4, it is 37 degrees. Okay, so now what he is saying is this circuit is capacitive in nature. Why is it capacitive in nature? So the 2 phases, right? Let's say the voltage is here, right? This one is behind by 90 degrees. That one is forward by 90 degrees. Now they cancel each other, but in this case, the capacitor trumps the inductor. Because the capacitor trumps the inductor, you end up with this idea that the whole circuit is net capacitive. Okay, time lag between the current and the voltage, is 1.6 milliseconds. Okay, so when does the current reach the maximum? When does the voltage reach the maximum in that periodic sine wave, right? So you already know the in this case, because it's 400 radians per second, right? So you write that omega equals 400, omega equals 2 pi f. Then therefore from that you derive the difference between the current and the max current and the max voltage. Okay, so I will come back to this question next time. As we have run out of, if we go and keep doing problems, then we'll get too fast, and then we also have to deal with the LCR circuit. So I'll start with the LCR circuit, and we go ahead and do some of the other problems. Okay. Now, my advice to all students with dealing with AC circuits is do a lot of problems. AC circuits is not that difficult. Okay, AC circuits, particularly RLC, basically what you have to do is you have to get a nice textbook like H.C. Verma and read H.C. Verma, and you will do very well. And then listen to some of the lectures. So typically what you should do in for AC circuits is you should listen to the lectures, look at the slides, and then you should read the textbook. Do it in that order. You already listened to my lecture, then now go and take a look at the textbook. Okay, if you go directly to just the slides and then do problems, things will get a little messy. You should spend some time listening to a lecture, because the idea is not that complicated, but they are not that simple either. Okay, so that's why I would recommend you getting either read the NCERT book, which is pretty good. Otherwise, you read the Concepts of Physics Part Volume 2, and then after, otherwise read the NCERT book will explain very well, you know. And then, but between this and that, you listen to the IIT PAL lecture or this lecture, you know, and then you go there. Okay? Now IIT PAL is better because they take more time. They are very deliberate and in their teaching, much more formal also in their teaching, and they get it very right. So you must understand this idea of phase. You know, phase is a fundamental idea when it comes to AC circuits, and phase is introduced by these secondary elements like inductors and capacitors. Okay, and with that, I am going to stop for today. We will continue AC circuits next class, but this is the prep that you have to do. You have to read H.C. Verma, read the full chapter. You know, I'll give you the chapter number also, so that you know. Otherwise, you get your you know, NCERT textbook and read the full chapter there. You will do just as well there. Alternating current is chapter 39 here, you know, and so he then discusses some of the details of you know, all these dynamos and also. Okay, so you know, we are fast approaching a time when but I think the material as dealt with in IIT PAL is better. You know, they are more thorough and cleaner. Okay, so try to understand that you know, before we then move on to additional material. You know, the remaining chapters, there's electromagnetic waves, and then there's a lot of modern physics. Okay, modern physics is tough if you don't read the material, otherwise not that difficult. Okay, modern physics is worth learning carefully and well. Okay, but you still at a high school level, they teach it, but they teach it with a view to give you an overview of the material, but this stuff, you know, they do give you enough to you know, get a good basis for the material, and you can then you strengthen your concept by doing more problems. Okay, and so, but then cover all the material. Go for 100% learning with respect to physics. Okay, then you have to do a lot of problems in the areas that are emphasized. Okay, and you have to build a very good conceptual understanding, and then that will really help you if you're taking the NEET exam or the JEE mains. You know, the JEE advanced, you must do even more. Okay, so particularly for this material, and you must get all these kinds of questions right. Okay, so with that, I'm going to stop today. I will see you again next week. If it's Sunday morning in India, then you're with me and you're learning a little more physics each time. All right, so with that, I'm going to stop, and I'll see you again next week.